Okay, now it's time to do a surface integral that integrates a vector field over a surface. This is different from integrating a scalar field over a surface because now you have to interpret the thing you're integrating as a vector that can either be normal to, parallel to, or something in between the surface that you're looking at. One of the big differences when you do integration of a vector field is that you have to look at the orientation of the surface that you're looking at. So that's why this specifies an orientation. The surface is going to be oriented in the direction of the positive y-axis. What you're probably becoming familiar with now is that we have to go and grab a bunch of ingredients here. So you've got to find a vector equation to describe the surface. You've got to find the partial derivatives of that. You've got to take their cross product, blah, 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 blah. So let's get started on those pieces. And the pieces will, at first, go like this. We're going to parameterize this surface. So S will be described as X equals, remember this, R cosine theta, but R cosine theta gets the R replaced with rho sine phi. So this turns into rho sine phi cosine theta. And we can do a little better than that because we know that rho is 5. Because after all, this has a radius of 5. Likewise, y is going to be R sine theta, but that's going to be 5 sine phi sine theta. Z, which we know is in principle is rho cosine theta. In this case, it will be 5 cosine, wrong angle. It's cosine phi, 5 cosine of phi. Okay. So we're going to use these to get R phi cross R theta. So first we'll get R phi. This is going to be just one component at a time, differentiate them with respect to phi. 5 cosine phi cosine theta, 5 cosine phi sine theta, and negative 5 sine phi. And then our theta will be one at a time now, negative 5 sine phi sine theta, 5 sine phi cosine theta. And because the z component doesn't have any anything with theta, this is simply 0. Okay, so we have our first really big ingredient to get here, which is R phi cross R theta. When we integrated scalar fields over a surface, we would find the magnitude of this cross product. That's not what we're going to be doing here. So this, by the time we get to the end of this step, we will have a fundamental thing that we're actually going to use in the problem. We don't need to develop it anymore. It does take a little while, though, just because, it's a cross product. So let's get a nice big roomy space to write this, I, J, and K. And the R phi is 5 cosine phi cosine theta. The J component of that is 5 cosine phi sine theta. And then the K component is negative 5 sine phi. R theta is negative 5 sine phi sine theta. The J component is 5 sine phi cosine theta. And the K component, thank goodness, is 0. I'll probably need more space than that. For the I component of this determinant, we're going to do this times this, which zeroes out, minus this times this. Minus a minus is a plus. So this will be plus 25, and then we've got sine squared phi times cosine theta. That's the I component. Minus the j component, which cuts these out and does this times this. Again, another 0. Minus this times this. Now pay attention. You've got 1, 2 minus signs here, but you're also subtracting it. So the result of this is going to end up being negative. Then when you combine it with this, it's going to end up being positive. But we've already written down that minus sign. So let's write another one on the inside. 25 sine squared phi sine theta. That's the j component. Add the k component and ignore these. This times this minus this times this. This is the hard one because nothing zeroes out. So we've got 25 sine phi cosine phi cosine squared theta minus the negative here means plus. So plus 25 sine phi cosine phi sine squared theta. And that right there is the k component. But we've seen this before. When you parameterize a sphere, the k component of that cross product is going to have this nice convenient cosine squared plus sine squared thing that factors out. I didn't want to skip right to it because, I thought that would be unfair, but this is going to be 25 sine phi cosine phi. Okay, so this right here is the k component. I'm also going to, at this point, turn these into plus signs because after all, they do have a double minus. So that's going to be just regarded as a positive number. At this point, you need to stop and take a look at the orientation of this because this is a stand-in for the usual unit normal vector that you use in the integral. And the unit normal vector is the thing that determines the orientation. So check out the orientation of this thing. We have the portion of this that has positive y values, and we want the orientation to be in the direction of the positive y-axis. So what that means is that we've got this thing here, this hemisphere, which not the best artist here, but that's meant to exist in the XZ plane. And then it also bows out, obviously, into the portion of space where the y-axis is positive, and it's, in a sense, above, as concerns the y-coordinates, this thing here, this hemisphere. But we want this to be oriented as well. And the orientation has to be that the normals are pointing in the direction of the positive y-axis. So we want the normals to be like that. We're going to do a couple things at once here. We're going to get a feel for what the bounds of integration are going to be. And we're also going to determine how this fits with the orientation question in the first place. Keep in mind that we want to orient it in the positive y direction. That means that this right here, this is going to be the important one for determining orientation. Now, why is it important? Why am I circling that one specifically? It's because it is the j. It is the j component. So it's not the same in every problem. You have to look at each problem individually. The reason that the j component is the important thing in this problem is that we want the orientation to be in the direction of the positive y-axis. That means that this must be positive over the domain of integration. Well, you look at it and you say, oh, well, there's a plus sign. You know, it's already positive. Not so fast. It's a little bit more complicated than that because we have to make sure that for the values of phi and theta that this function will adopt over this domain, it remains positive. And you'll remember that trig functions can sometimes end up being positive and negative in ways that you don't expect. So to decide this question, we have to say, what's the range of values that phi and theta will cover over this domain? Well, we know that we're starting on the positive z-axis, and I put that dot a little too high. We're starting right there, okay? So this we can think of as the beginning, and then we fold down off the z-axis to form this hemisphere. You can fold down in any of these directions, but you are folding from the positive z-axis down to the negative z-axis. Now, I want you to think about what that means in terms of an interval of phi values. Phi here goes from 0 up until pi, because if it covers this range of values, that is from the positive z-axis all the way down to the negative z-axis, and that's exactly what we want. But we also need to decide an interval for theta values. Now, think about it. Theta begins at 0 on the x-axis right here, okay? The positive x-axis. And then it folds up here until the point where it gets to pi over 2 and then gets to pi over here. If we allow phi to go from 0 to pi, and it goes through all these possible paths, and we also allow theta to go from 0 to pi right there, then we will have covered this domain of integration. So theta is going to go from 0 to pi. These are the bounds of integration. Now, over that domain, we can say, is 25 sine squared phi sine theta positive for these values? One of these questions is very easy. We have to look obviously at the phi and the theta separately. For the phi, it is simple because for the phi value, it's always positive because it is sine squared of phi. So that's not going to be an issue. For the sine of theta, that's where you actually have to ask the question. But luckily, for this domain, theta going between 0 and pi, we know that this means sine of theta is between 0 and 1. Like it begins at the positive x-axis, ticks up to the top of the unit circle, and then winds back down to 0. So it goes from 0 up to 1, and then back down to 0. It's 0 at the end points, but in the meantime, it's completely positive. And that means that this is good. This is what we want. If it weren't what we wanted, it would be okay. We would just take the reverse of this entire RU cross RV. So because yes, no sign change is needed on RU cross RV, and in this particular case, RU and RV are R phi and R theta. Okay, so this right here, R phi cross R theta, it's usable as is. Again, if we had found that the orientation was the wrong way, we would fix it by applying a minus sign to the whole thing. That's not rigging the game, it's just playing by the rules. So now the next step is that you need to form the actual integrand. So we need to form f dot r phi cross r theta. And this needs a background task. This is what is f in the first place. We know that f of x, y, and z is, and you can scroll up and see, it's xz, x, and y. xz, x, and y. But the parameterization means that now we're going to be thinking of x, y, and z as functions of phi and theta. You usually don't write it this way, but just to drive it home. And this is equal to xz. Well, x is 5 sine phi cosine theta, and z is 5 cosine phi. So this will be 25. The x gives us sine phi, the z gives us cosine phi, and the x gives us cosine theta. Now for the x component, or rather the j component, which is x, that is simply 5 sine phi cosine theta. It's simple because all that needs to be done is to copy the x component of the parameterization. The z component, or the k component, is y, and y in this parameterization is 5 sine phi sine theta. All right, so f dot r phi cross r theta is, now we're going to be taking this thing right here and forming its dot product with this whole nonsense up here. So let's see. I'm going to grab this so that I can reproduce it down below. All right, I'll get rid of that in a minute, but just so that I've got it right in front of me, this is going to be this guy times this guy. So that will be 25 times 25 is 625 sine cubed of phi cosine of phi cosine squared of theta. So now these two are taken care of. That part of the dot product is done. Now it's plus this guy times this guy. Plus 5 times 25 is 125 sine cubed of phi once again. Sine of theta cosine of theta. Yes. All right, next component. This times this. And once again, 5 times 25 is 125. Sine, not cubed this time, but just squared. Sine squared theta, or sine squared phi, times cosine phi times sine theta. Okay, that guy can go away now. And then the integral, which we finally get to write now. The integral is the integral over the two-dimensional domain of this dA. I'm going to refine this a little bit. I can factor out a 125, first of all. I do know the variables of integration. They are phi and theta. They both go from 0 to pi. And with that factored out, I now have 5 sine cubed phi cosine theta, or cosine phi, I always make that mistake, times cosine squared theta, plus the whole 125 has been factored out, so this doesn't have a coefficient anymore. Sine cubed phi times sine of theta cosine of theta plus sine squared phi cosine phi times sine of theta. And this is d phi and then d theta. Because this is such a big and ugly integral, instead of trying to tackle the whole thing at once, I'm going to do them in 3 pieces. I'm going to say this one will be the first piece. That's right here. And then the second piece will be right here. And then number 3 is going to be the rest over here. For number 1, let me see, the inner. Yes, we are going to need to do an inner and outer for each one of these, but don't worry, it actually ends up being a little bit better than it looks like it's going to be. For the inner, we can say u equals sine of phi, making du equal to cosine phi, d phi. All right, and then the integral becomes, well, let's get the bounds of integration as well. U of 0 is 0, and u of pi is also 0. Oh, well, that's nice. Watch out for this, because the only reason that's going to work, like it's going to yield some nice benefits, but you'll see that there's a trick to why it works. It's because this integral is expressible in terms of this u and this du. If you just select whatever u you want and you're left with variables left over, like that are not cleaned up, you didn't do it right. So this is going to be integral from 0 to 0, and that's not a mistake because I am copying these, but it's integral from 0 to 0 of 5 u cubed times du. And then just to keep myself honest, I do have to copy the cosine squared theta from there. But you can see what's going to happen now. Integral from 0 to 0, this is an integral over a single point set that is always equal to 0. So the first integral is 0. The second integral, like I don't even need to progress to the outer version of this integral because in the inner it's already 0. And so I know that the outer would necessarily be 0. For integral number 2, for the inner, I don't get to use the same u substitution because it's not sine cubed phi cosine phi. It's sine cubed phi, and then later on there is a cosine, but it's of theta. So yeah, we're not going to get away with it. We're going to set sine cubed of phi equal to sine squared of phi times sine of phi. 1 minus cosine squared of phi times sine of phi. And you can probably see that we have the goal of doing an integration by substitution. So then if we set u equal to cosine of phi, du will be negative sine of phi d phi. U of 0 is 1, and u of pi is negative 1. We saw this when we integrated the scalar field over a surface. This is going to be one of those things where the integration bounds are like, topsy-turvy. So this will give us an integral from 1 to negative 1. Again, this is not a mistake. It is from 1 to negative 1 because it was 0 to pi. 0 turned into 1, pi turned into negative 1. You have to be honest about it. So this will be 1 minus u squared times, times negative du. And at this point, I've accounted for all the phis. So now it's going to be sine theta, cosine theta. Now I'm going to do two things at once. I'm going to bring this minus sign out to the front, but I'm also going to reverse these limits of integration so that it becomes more familiar. And that, of course, is going to leave me with minus signs that cancel out. So this will be from negative 1 to 1, now, and 1 minus u squared du, again, times sine theta, cosine theta. It is, of course, u minus u cubed over 3 at negative 1 and 1 times sine theta, cosine theta. and that is equal to 1 minus a third minus -1 plus a third. And that whole thing times, yes, the same thing as before. 1 minus a third is 2/3. -1 plus 1/3 is -2/3. So this is minus -2/3 for plus 2/3. And then that is times the same thing as before, which equals 4/3 times sine theta cosine theta. This is a non-zero term. So it's going to be easier if I carry through this integration to write this way. First of all, you should know this one. Sine of 2 theta is equal to 2 sine theta cosine theta. And this looks quite similar to what we have here. So I'm going to divide both sides of these by 2 to get this identity. Sine theta cosine theta equals 1/2 sine of 2 theta. And this is much easier to integrate. So this will be 4/3 times 1/2 sine of 2 theta. But then that, of course, reduces these so that you end up with, that becomes a 2, and you have 2/3 sine of 2 theta. For this one now, we do need to do the outer. We're still on the second integral. The third one is 0, so don't worry, it's not going to be too bad. So the outer, I didn't tell you that. Just pretend I didn't tell you that. So the outer is from 0 to pi of 2/3. So let's bring that out the front. Sine 2 theta d theta. Nothing fancy here. 2/3 times, well, the integral of sine is negative cosine. So this will be negative cosine of 2 theta over 2 because of the chain rule from 0 to pi. 2/3 times negative cosine of 2 pi. Cosine of 2 pi is 1. Negative of that is -1 over 2. Okay, and then the 0 one. So this will be negative, or minus rather, and let's see, cosine of 0 is 1, but it's minus -1, so that will be plus 1 over 2. 0. Seriously? Wow. Okay. Well, I must have been remembering that one when I thought about this, because I did work this out ahead of time. Okay, the third integral. Everything else has been 0 so far. So maybe we'll luck out, and this will be 0 as well. We're looking at this. Sine squared phi cosine phi times sine theta. Sine squared cosine, for the inner integral from 0 to pi of, I believe this was it, sine squared phi times cosine phi times sine of theta. Is that right? Sine squared phi cosine phi sine theta. Yep, bingo. It's worth checking. D phi. All right, so you can see that we're going to do a u substitution here. This will be u equals sine of phi, making du equal to cosine phi d phi. And for this, I'm going to just say du is right there. So I'm not going to like solve for d phi and all that stuff. So we now need to do the bounds of integration. U of 0 is 0. U of pi is also 0. We've seen this before. So if we can make this integral expressible in terms of u and du, then we'll be good. Is it expressible in those terms? Integral from 0 to 0 of u squared du. Here's your u squared, and here is your du. That's then going to be multiplied by sine of theta. Because the integral is expressible in terms of u and du, and it's integrating over a single point set for u, that integral is going to be 0. And so this ends up being 0. And once more, you don't need to progress to doing the outer integral because the inner one is already 0, and the integral of 0 is always 0. So what have we learned here? Well, originally, it was 125 times this double integral over the domain of blah, 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 d phi d theta. We split this into 3 pieces, 1, 2, and 3, but all 3 of these are 0. So this ends up being 125 times 0, or just a big fat 0, which I always think is kind of disappointing because I want my hard work to yield something other than 0. But hey, it is the right answer, so I'm not going to complain too much.